let's look at this question. Methane gas, 4.50 grams, occupying a volume of 12.7 liters or decimeter cubed at an initial temperature of 310 Kelvin. This time it's expanding isothermally against a constant external pressure until the volume changes by 3.3 decimeter cubed or liters. But the gas is not behaving as a perfect gas, so anywhere in the past where we've made the assumption that PV is equal to nRT is not applicable here. The gas is a van der Waals gas. And so we should be consulting a data sheet, and I've gone and collected some information here on this gas, and I've got the van der Waals constants, A and B, and I know that the internal pressure, pi sub T, is about equal to A over molar volume squared. More on that later. I've looked up its CP value. I added the isothermal expansion coefficients and compressibilities, but values for them. Yeah, lots of constants, things that we don't need for this question, but anyway, some second virial coefficients, sigma, which is our collision area, cross-sectional areas, some critical temperatures, pressure, volume, boil temperature, and molar mass. But most importantly, as soon as we see that a gas is a van der Waals gas, then we want to make sure that we have the A and the B. The pi sub T internal pressure will be important here, and if you're doing this question on your own as an assignment and using maybe online resources to find the internal pressure, you may find it difficult. So what's nice is to know that it can be approximated for a van der Waals gas as being equal to the A over Bm squared, which is that second modification of the ideal gas equation of state that van der Waals proposed. Okay, so I'm going to take those out of view, but that is my resource that I've created, and of course in an assessment situation you would have access to that information in the form of a data table for any number of gases. It's not necessarily given in the question. And just a note on how this question is given, just for the sake of efficiency in this tutorial, it's already laid out in a nice given format, and what we are asked to find is here. But as you know, in questions on assessments or at the end of a chapter in a textbook, they're written out as in paragraph style. So it's a very important step that you shouldn't skip, and that is to look at the wording of the question and extract out what it is that we are given. And so in this case, it is methane. It's a closed system. Methane is behaving as a van der Waals gas, so it's a real gas. And so I have the mass, and with a molar mass, I can of course find the number of moles, and that'll remain constant during this isothermal change. The volume is equal to the initial volume plus the difference, and the difference is a positive 3.3 liters. And the temperature is staying the same, and so T2 is equal to T1, and that's given as 310 Kelvin. The pressure, I don't know, but I want to remind myself that pressure is the van der Waals pressure. And so I'm just going to write out my formula here, which you should know, the formula for the pressure for a van der Waals gas. And that formula is equal to what? The ideal gas equation of state P is equal to nRT over V. But for a van der Waals gas, what is that formula equal to? So think about how the internal gas equation of state. Just going to get all my data ready. Think about how the perfect gas equation of state was modified. So P is equal to nRT over V. In terms of molar volume, I could write that as P is equal to RT over Vm. And so P van der Waals is equal to RT over, remember the Vm is modified, and we take away from that and account for the attractive forces, and a good way to remember that was A for attractive forces, and that was A over Vm squared. So my two van der Waals constants are V and A, and again I just showed you that those are given somewhere else in the data sheet. Excuse me. So your molar volume is going to be your volume divided by your number of moles. Sorry about that. Yeah, and I also showed you just a moment ago that that pi sub T, the isothermal internal pressure, and it was about equal to A over Vm squared for a van der Waals gas. Well, just remember, I'm going to get another sheet here, piece of paper, just to explain that. Okay. That pi sub T, do you remember what it is? It was called an internal pressure. So that gives me a clue as to its units. But it was the rate of change. Joule tried to do this in his experiment. He tried to measure the change in internal energy when a gas expanded. And he was holding the temperature constant by immersing this flask that he was working with in a big reservoir, basically. So he was looking for any change in internal energy as the gas expanded. And we know that for an isothermal, and that's what the T outside of this rate of change means, it means it's being held constant. So when I change, when I measure my condition, it's kind of an experiment, isn't it? So, this would be, you know, the slope of the data that you're collecting. So we know that for a perfect gas, an isothermal change on a perfect gas means that the change in internal energy is going to be 0. So that's why this guy is 0 for a perfect gas. But this is a van der Waals gas, and that means that, you know, for those gases in these cylinders, those particles actually have an attractive force exerted on each other. So if you think about expanding this volume, you have to pull these guys who like each other apart. So that's going to take some work to do that. And work is a form of energy transfer, so that's going to affect the internal energy of a gas. So you can imagine that the internal energy is probably going to drop if you've got some attractive forces in the gas. And methane, in this case, is an easily compressible gas, so I wouldn't be too surprised to find that that would be positive value. So that's what this equals. It's the rate of change of internal energy with a change in volume isothermally. And so, of course, that is equal to 0 for a perfect gas, like we just said. And I would look that up in the table here for methane, because it's behaving as a van der Waals gas. It's a real gas. Can't find it, but what I do find is that it's about equal to A over Vm squared, right? And we just wrote out the van der Waals equation for the pressure. Let me just rewrite it again here. RT over Vm minus B. Now think about this. If I just covered that, there's your real gas equation of state right there. PVM is equal to RT, or PV is equal to nRT, right? But the molar volume, because the gas particles exert an attractive force on each other, is maybe a little less than, the observed one is a little less than predicted ideally, so that accounts for that. And because that's going on, maybe the pressure exerted by this gas is a little less than predicted ideally, and so we have to take a little bit away from the pressure as well. You might be thinking, well, what about the gases that actually have net repulsive forces and not attractive? Well, this is written in one form, and it kind of takes the perspective of attractive forces dominating. And so this is why A and B can be positive or negative. So we have one equation, one set of constants that account for both net attractive and net repulsive forces in gases. So the pressure might be a little bit less than observed if these gas particles have attractive forces on each other. And so we see that this little term here is taking away from that which otherwise would be predicted. Or modified slightly, but not completely, to account for these attractive forces on the molar volume. So, or on the pressure. And this term here is this term here, and so when the gas is a van der Waals gas, this is about equal to this, because they're really accounting for the same thing. So don't look for pi sub t if it's a van der Waals gas in your data sheet. Probably not going to find it, but what you will find are the van der Waals constants A and B. So we need to know that this will suffice for your internal pressure value, pi sub t, for a van der Waals gas. So when you have A and you have information on the molar volume, then you have enough information to calculate pi sub t. Okay, and that's what we're doing in this question. So back to it then. So I think we can determine, we have enough information hopefully to determine the heat, the work, and the changes in internal energy, enthalpy, temperature, volume, and pressure. And we'll circle these maybe as we go along. Okay, I'm going to do the easy one first because it's isothermal. So I'm going to say, look, it's isothermal, delta T is equal to 0 because the change is described as isothermal. So let's cross that one off. Start with the easy stuff. Now, if this were a perfect gas, I would move right away to delta U being equal to 0, but it's not perfect. It's van der Waals. Okay? And delta U is not equal to 0. It's still equal to the sum of the heat and the work. So there should be some work because it's expansion. And again, just to compare with what is a more frequent scenario we're given, if this was a perfect gas and this guy was 0, sorry, then Q and W would be equal and opposite, and I would, find the work and then change the sign and have the Q. But again, this is not a perfect gas. It's van der Waals. So what's going to be my plan of action? I could find the work right away. There's no formula for me to do the heat. There is one for delta U. Okay, so I can find W and I can find delta U, and now I'm back to a nice situation where I have one equation and one unknown, so I'll just work with differences to find Q. So that's the plan. Okay, so yeah, the work will be straightforward. So let's do kind of straightforward van der Waals pressure. I think we have enough, information to do delta U. So let's do the delta U first. So what does it actually equal? Okay, let's go down a dead end because this is a tutorial, and so let's make some mistakes and learn from them. So I know that du is equal to m CV molar dt. Is that going to help me here? Think about that. I'm having a sip of coffee while you think about that. it's not going to help us because it's isothermal. And that dt is going to be 0, and that's going to make this 0, and we're back to the condition where that was true. Delta U is 0 for a perfect gas. And so that's not a good way to go. I don't really have anything else for delta U that I can think of. So we'll start. U here is a function of temperature and volume. And that means that any change in internal energy is equal to change due to a change in volume. So this, because of volume, holding the temperature constant, remember, this is called expanding the differential, times that change, plus the change in internal energy due to a change in temperature, holding the volume constant, times that. Now, these rates of change are sometimes their own properties. du by dv, a constant t. How does the internal energy change when we change the volume and do so isothermally? That is I sub t. And this, do you recognize it? du by dt, constant v. That's actually a dq, because it's constant volume. Right. That's a CV molar. I'll just write CV for now. Yeah, so if I wanted to plug into this on the finite change, delta U, that would become m CV molar delta T, right? Because I would need the number of moles there. But I'm not even going to take it that far yet, because this is equal to 0 because the process is isothermal. And so my infinitesimally small change in internal energy is equal to I sub t dV. Integrating it, I get delta U is equal to the integral of my pi sub t dV. And I'm going to assume that this internal pressure variable, is constant, that it is constant, over my small volume range. And the integral then of dV is just simply delta V. Okay, now let's apply what we've been told about what that equals. A over molar volume squared times delta V, which is given. Let's move this way to make our solution equation. So A was equal to, don't know if that's a 4 or 14. Just going to look up A for methane again in the textbook. So if you're doing this as an assignment, it's in the back resource section. And we have second variable coefficients, collision cross sections. I'm looking for van der Waals constants. I don't see them yet. And over here, sorry about this. That's all the thermodynamic data. Let's come afterwards. Here's my alpha, so campus conversion. Fugacity. Oh my goodness. I don't want to stop the video and I don't have an opportunity to pause. Oh, here they are right here. No. Van der Waals. Oh, it's right here. And so, I'll just show you. So for methane, CH4, A is 14.61. Okay. Put that out of the way. 14.61, and the units were atmosphere, decimeter to the sixth, and so decimeter to the sixth is the same as liters squared. And I just want to use liters per liters squared per mole squared. Sorry, dropping everything. Yeah. Now the molar volume. The volume is 12.7. Decimeter cubed, or liter, and that's going to be divided by the number of moles, and the number of moles is 4.50 grams times 1 mole, which is 16.043 grams. Now all of that is multiplied by the change in volume, 3.3 liters. This A over BM squared should actually have units of pressure when all is said and done. So this big term should have units of pressure. So grams, oh, right here, this is a molar volume squared. So grams go out with grams inside those brackets. This is a liter squared and a mole squared. I'm leaving this here because it's still going to act on the number. I'm left with atmosphere. It's going to be multiplied by liter, so I'll have liter atmosphere, and I really want energy in joules. So I'm going to add to this in the one-step solution line and multiply it by 101.3 joules per liter atmosphere. That's a conversion factor we've been using a lot of lately. Okay, so get your calculators out, and I'll just carry on and indicate that my final answer is in joules. Okay, I'm going to do this bottom part here first. 12.7 divided by 4.5 times 16.043. So I have a molar volume of 45.2769. So I'm just going to double check that. So the number of moles, I'm just going to add that to the top. Number of moles is 0.280496. So 0.280, and then I put the 5. That's my number of moles, in case I need it again. And 12.7 divided by that 0.28 is the 45.28. That's my molar volume. So now I need to square that. And then I'm going to take its reciprocal and multiply it by 14.61. So for this term here, I've got 0.007124. I'm going to carry on, multiply by 3.3, and then multiply again by 101.3. And I get a delta U. And before I write this down, are you expecting a sizable value or a small value? Perfect gas would be 0. This van der Waals gas, probably not too far off. So I am expecting a rather small value for delta U. Okay? And that is equal to 2.38 joules. So there's my delta U. And I'm just going to put a circle around that as having been found. Great. So now let's do the work. Did you still want to see that? I'll just leave that in view. Okay, let's do the work. Work is equal to a minus, or dW is equal to a minus P dV. Always a common starting point. And in this case, that's going to integrate to being equal to a minus P external delta V. Again, we know delta V, and in fact we are given also the constant external pressure, so this should be, no we're not, I'm thinking of another question. It's a van der Waals gas. We don't know what that is, but we do know what that is. So the delta V is 3.3 liters, but we don't know what the constant external pressure is. But remember that it is equal to the P final of the gas. Okay, you know that. You're not explicitly told that in the question, but you can safely deduce that. So what is P2 of the gas? I can't use PV-nRT. Remember, it's not a perfect gas. It's a van der Waals gas. So P2 of the gas is RT over, it's the van der Waals pressure. That's what it is. So the work is equal to, and that's going to be my molar volume in the second case. So let's just go up here for a moment, back to the given. V2 is equal to V1 plus 3.3, and that is equal to 16.0 decimeter cubed or liters. Okay. So, and I'm going to use that N value that I calculated earlier. Okay, so go ahead and do this. I'm going to do this here on my own. I'm just going to write it out again. RT Vn minus B A over Vn squared, and all of that is equal to, multiplied by a delta V. Big equations. I'm using the 0.08206 value for R. Temperature is isothermal at 310 Kelvin. All of that is over my molar volume, which is the volume divided by the number of moles. This is V2 volume, so it's 16.0 liters divided by, we calculated the number of moles, 0.28046. And yeah, that's too many sig figs, but if I had done the calculation in the calculator, that's the number that would be stored. So I'll trim at the very end when I do calculations that are all multiplication. Okay, that's my Bm, and then minus B. I'm looking at the data sheet again, and B was 4.31 times 10 to the minus 2 liters per mole. Liter per mole, good, because it's subtraction after all, I have to have the same units. All of that, is this first term. And then I have a minus A over Vm squared, which is what I just did up there. And I can't fit it in on this paper, so I'll keep going. Yeah, we just calculated it up there, and I have a value, but anyway, I'm going to write it out again for you. 14.61 atm meters squared over mole squared. That's all over the molar volume squared, and the molar volume is 16 liters over 0.28046 moles squared. And yeah, so again, that is not correct. I had just done that up there, but I had done it for the initial state conditions and not the final. That would have been an error if we just transferred that value down. Close the bracket and then multiply by the delta V, which is the 3.3 liters. So I need the term inside the square brackets to come out as atmosphere times liter, and then times 101.3 joules per liter atmosphere, and that'll give me my work in joules. So let's go through and look at the units. So I have liter atmosphere on the bottom as a result of that difference here. Liter, did I say liter atmosphere? I'm sorry, liters per mole, liters per mole. And that'll go out like that, and I'll have atmosphere and Kelvin. Ah, look, liter atmosphere per mole Kelvin. I was missing the Kelvin on the R term. So Kelvins go out, and the liters per mole will cancel with the denominator units, and I will be left with atmosphere, so that's good. And then the liter squared and mole squared will cancel with these, and I'll be left with atmosphere. I have a difference in atmospheres, so that's still atmosphere, times liter, that'll go out with this, and I will be left with joules. So I'm not going to go through and slashing everything, but I will be left with an answer of joules. So now we just have to plug everything into the calculator. So this is the boring part for you to watch on the video, so why don't you do that on your own. I'm going to figure out this denominator first. So 16.0 divided by 0.28046. That's 57.049. That's my molar volume in the second state. And I take away from that 0.0431. And that's 57.00 on the bottom. I'm going to take the reciprocal of that and then multiply it by 0.08206. It just allows me to keep going with the calculator. And multiply again by 310. Okay, so this whole first term, now I have a value of, I'm just going to jot it down up here, 0.44624. That's that whole first term. Now this, so 16.0 divided by 0.28046, again, that's the 57.049 molar volume. I square it to get 3254.6. I take the reciprocal of it so that I can continue my multiplication in the calculator, and I multiply that by 14.61, and I get, I was expecting this value is always really small. That's 0.004489. Okay, so now I've got my two terms inside my square brackets. So I'm going to make this, which is still in the calculator, I'm going to make it a negative value and add it to 0.44624. So my term now inside the square bracket is 0.44175. I am now going to multiply that by the 3.3 to get 1.45. Not very much work, but that's liter atmosphere, and then multiply by 101.3 to get my final answer for work. Hopefully you have the same thing. Hopefully I've done this correctly. And I want to go, you can't see, I want to go all the way back here and remind you that that negative sign needs to be carried through. And so work is a minus one. The answer is 147.67, so I'm going to write it as 148. And that's my value for work. Okay, bring this back down. So now I have work, and Q plus W is delta U. So now I can find out what Q is. I'm going to use this little bit of space that I have here. Delta U is equal to Q plus W, therefore Q is equal to delta U minus W. Let's go up here for a second. So Q is equal to, what did I have for delta U? 2.38 joules. And for work, so minus work, but work was a negative value, 148 joules. You still see that? So minus a negative is plus a positive, and 148 plus 2.38 is 150.38. But I have no decimal places on here, so my answer should be with no decimal places. So 150.38 is rounded to 150. And there's my value for Q. Great. Really small difference. Remember, those are equal and opposite if it's perfect, but this was a van der Waals gas, and the delta U was super small with just 2.38 joules. So now I have Q. Okay, what about the other ones that we still have to do? Delta H. What about delta H? How do we find that? Searching for another blank sheet of paper and kind of running out. Well, what's always true, regardless of the change, is that H is equal to U plus PV. And so my delta H is equal to delta U plus the delta of PV. Now, PV is a constant for an isothermal change when it's a perfect gas. And when it's a perfect gas, I can substitute this out for nRT. And so that would be nR delta T, and delta T is 0. But it's not perfect. It's van der Waals. So what am I supposed to do? Well, I have delta U, so that'll be fine. I can give the number there. But this guy here, delta PV, is P2 V2 minus P1 V1 after all. And this is a van der Waals gas, but it's worked against a constant pressure, and that pressure is the P2 van der Waals. And so P2 is, so it's worked against. So I'm doing this, and this pressure is my van der Waals pressure, RT over Vm minus B minus A over Vm squared. And we just found that. We actually just found that when we were calculating the work. Let me just throw this back here and make sure that you agree with me. For the work, we said it was equal to a minus P delta V. I didn't carry the negative sign there, but we did add it at the end. And that, in the square brackets, was the P final of the gas, which is P2, the van der Waals P2. And so there's my P2, there's my delta V. So wouldn't you say that this work of minus P delta V is actually this guy here, P delta V? It's the same, isn't it? Okay, so this is P delta V, where that P is the P2 of the gas, which we just said was equal to this guy for the second equilibrium state, the final state. And we just found that that term inside the square brackets was equal to 0.44624 minus 0.004489. Yeah. So delta H is equal to delta U, which we just found as 2.38 joules, plus P2 was equal to 0.44175. Yeah, I'm carrying all the digits here because they're in the calculator. Atmosphere. Where did that number come from? Right here. Inside the square brackets is P2. And I had written down that the term, 0.44624, the value of that first term, minus the value of that second term. And that answer is, that difference is 0.44175. And that's multiplied by delta V, 3.3 liters. And I have to multiply it by 101.3 joules per liter atmosphere. So delta H is equal to 2.38 joules plus, so we had 0.44175, keep going with it, times 3.3, but that's liter atmosphere, so times 101.3, and we have this, 147.67, joules. And how many sig figs should that be? Just 2. That should be just 2. So I think, yeah, because of the 3.3 liters. So 150. And then it should have no decimal places. So delta H is 152.38 joules, rounded to no decimal places. It's 152. Okay, that's our delta H. Go back up here. That's done. Delta V is given, 3.3 liters. And the change in pressure, oh dear, it's a long question. What is P2? It was expanding against a constant external pressure, that's true, which is equal to P2 of the gas. But we don't know what P1 of the gas is. So, I'm losing my voice. Delta P is equal to P2 minus P1, and these are both van der Waals pressures. Yeah. So, I have to move it over here to make room. I'm pretty sure that we have a value for P2 that we've just calculated. But I'm just going to write it out. So that's your RT over Bm2 minus B minus A over your molar volume V over 2 squared minus RT, I'm not putting T1 or T2 because T is constant, over your molar volume initial minus B minus A over molar volume initial squared. And that's going to give you an answer in atmospheres. And I'm going to let you figure that one out so that this is not a 50-minute video. Some of you might be wondering, wow, that's an incredible question for a midterm. It would be the whole midterm. I'm looking at the clock here. It's 49 minutes right now. But we are really taking our time and we're being completely inclusive of all the things that we should know about this question, and certainly we wouldn't be able to ask everything of you in a midterm situation. Okay, so you're going to go ahead and do this. This R is 0.08206 liter atmosphere per mole K. This is temperature is 310 Kelvin. Your molar volume here is 12.7 liters divided by 0.2805 moles. The B value was 4.31 times 10 to the minus 2 liters per mole. The A is 14.61 atmosphere liter squared per mole squared. Your molar volume again is this guy, but it's going to be squared. And then over here, your molar volume, everything's the same except your molar volume. Your molar volume in the second case is Vm2 divided by N. And I'm looking back, I thought we had figured out what that was. Yeah, it's 16.0 liters divided by N's constant, so 0.2805 moles. Same B, same A, and that molar volume again, but squared. And you should have an answer in atmospheres. And it should be, what should it be? Greater than, less than, or equal to 0. It expanded, so you had an initial pressure, and it was in mechanical equilibrium, your system. And then the pressure must have been suddenly dropped to P2 in order for this system to expand until it equals P2 again. So we're looking for a pressure drop. And so P2 is less than P1. And so you expect this delta P value to be negative.